All right, let's get started. Good morning, everyone. My name is Mustafa Kogur. I've been with Delta Tau for 8 years. I'm one of the application engineer working in the tech support line. So you could reach me. I have a card over there. You can grab one. If you have any problem, you can reach me at that line. So today, the beginning Power PMAC class is over. These are the advanced class subjects. This Thursday and Friday, we're going to see advanced features of the Power PMAC. And one of them is the subprograms and subroutines. This is what I'm going to teach this morning. So let's get started with the subprograms. Power PMAC can execute subprograms other than motion programs and PLC programs. You can also call subprograms and execute whatever in the subprogram you want to do. So subprograms can be called from a motion program or a PLC program using the call command. Call and constant command, where the constant is a floating point number, let's say for example 100, and this is the integer part, which is the subprogram number. So with this one, you're calling subprogram 100, and the fractional part is the line number. But there is a 3, you need to times with 1 million. So let's say 100.00001 will be calling the subprogram 100 line number 1. So this part you need to times with 10 over 6, 1 million, to find the line number. And this integer part is the subprogram number. So that line number is shown as N data. So in this case, it's going to go to N1, right? In the calling program, it's going to go to N1. Subprograms can also be named or called by using the syntax call name, and then in parentheses the arguments you want to pass to that subprogram. So you want to call my sub, and then the arguments you want to pass in to that subprogram. You can also receive output from the subprogram to the calling program. Output arguments should be preceded by an ampersand sign. For example, call name of the subprogram, then you have the input 1, and then you have ampersand output 1. The subprogram will return that argument value to the calling program. Subprograms are executed and returns to the calling program at the call line upon encountering the return or at the end of the subprogram. So you can call the subprogram 100 line number 1, and then you can write a return and go back to the calling program. Or if you don't have the return, then it will execute all the way to the end of that subprogram. You can pass arguments to the subprogram and receive outputs from the subprogram. Can jump to lines within the same program or PLC by labeling the line number with the N data, where data is the line number again. It could be 0 to 909,999. You can issue a goto and a constant to go that line and continue on, ignoring the return. Or you can use goSub and constant to go that line and return to the calling position upon encountering the return. The trick is no argument is required. No argument passing is required, permitted in this goto or go sub commands. You can do argument passing with the call sub constant. It will jump to the line number where the constant, numbered within this program and permits the argument passing. So let's see an example. Probably you have used this one in the PLCs, right? Or in the motion program exercises. You have a timer example, open subprogram timer. This is in your library, right? You put this in your library. Open subprogram timer, the duration, you want to, wait in seconds. Local end time equal to sys.time dot duration, while sys.time less than end time, close. Okay, this is the example. We can do it in the class now. We have a subprogram which calculates the hypot of the triangle. You have two arguments, rise, run, and %hypot. This is named as Python, open subprogram Python. You have the local variables, rise, square root, run, square root. So rise square root is equal to rise times rise. Run square root equal to run times run. And the hypot is equal to square root of the sum of the rise squared and the run squared, and close. So it's an easy triangle hypot calculation, right? And in the motion program, this is our calling program now. This is the subprogram. This is the calling program. So now I'm going to pass the arguments to the subprogram, right? And I have declared this globally, global x distance, x dist, global y distance, y dist, and global vector distance, vec dist. And then I give the values for these distance. For x is equal to 3, y equal to 4. And the vector distance is 0 now. This is my output. And then I have defined a coordinate system, undefined all, and %1, open program number 2, and the call Python. So I'm calling that subprogram now with the name, right? I can call the subprogram with a name. And then I'm passing the arguments. This is the argument 1, argument 2, and this is my output. So I will receive the result with this vector distance. So now this 3 and 4 will be passed into this subprogram as rise equal to 3, run equal to 4, and then it will calculate the hypot, and then it will return the value to the vector distance. This is a call sub example. We're not going to do this example just to see how it works. We have a subprogram, open subprogram, my sample function with my input and my return. Then you define a local variable inside my variable. And then in the if statement, if my input equal to 1, it returns my return equal to 34. Else, it goes to a call sub.getTime, and my return. So if it's not equal to 1, my input, it goes to the call sub. It's called the sub.getTime with inside the program, right? So the call sub can work inside the program. And then you're checking with my input equal to 2. So if it's 2 this time, then you go to, again, a line. Jump down the line number 34 and execute until return is found. So you go to 34, line 34, you sign P1 equal to 36, and then return to this program. And if input is not equal to 2, then you then you just go to return to the calling program. Okay, so this is another subprogram example. Your subprogram and your calling program with the motion program 4 call 3.00001. That's going to call subprogram 3 line 1 times 1 million, right? The fractional part. This one is going to be line 10. This one is going to be line 100. And this one is going to be line 10,000. You need to times with 10 to the 6th. And then in the program, you need to number like this: N1, N10, N100, N1000, colon, and the motion command you want to do. So you can use the Power PMAC as a general automation controller in many applications, but you can also use Power PMAC as a CNC controller with this subroutine feature. So this enables you to have the Power PMAC as a machine tool controller. These are special subroutines in the firmware. So when the PMAC, when you make the PMAC work as a CNC controller, it will read the G codes, M codes, T codes, and D codes. And these are the standard RS-274 codes. And these subroutines is treated in the Power PMAC specially. So instead of times 1 million, this time you need to times 1,000. Whatever after the G, the number, you're going to times with 1,000. That's going to be your line number in the specific motion, the subprogram number. So for example, for the G, the subprogram number is always 1,000 until you don't change it. There is a structure I will show you in the next slide. You can change that. But if you don't change it, every time PMAC sees a G code, it's going to go to the subprogram 1,000, and the line number is whatever after the G times 1,000. So G73, for example, equivalent to call subprogram 1,000, line number 73,000. M03 is equivalent to call subprogram 1001 and go to the line number 3000. T01 will be equal to call subprogram 1002 and go to the line number 1000. D, go to the subprogram 1003, the line number 12,000. So you times with 1,000 after the letter to find the line number. But if you want to change those subroutine program number, which are the program 1000 through the 1003, you can change with the coordinate x.gproc, chord x.mproc, chord x.tproc, and chord x.dproc. So if you want to use some other program number, you can change it. But I don't see any reason to change these numbers, that they're in default program 1000 through 1003.
So all the G code, all the standard G codes and M codes are.
They're not there. You're gonna write the subroutine. Yeah. The integrator, I should say, they should interpret this G codes as they want.
Yeah.
We can give you the standard codes. Delta Tau can give you the standard list. So if you want to have a standard 3-axis milling machine, for example, we can give you the code for subroutine 1000. But the beauty is you can write your own code. So if your customer wants a special function in the machine, you can add that by creating another G code.
Yeah.
So in your CAD/CAM program, if you have a specific, there are many different CAD/CAM programs, right? They will output the code, and some of them are not standard. So, but you can adjust the Power PMac to accept that code. By you have the flexibility to add and change things in the subroutine because you're writing it. So once you write these subroutines, the part programmers or the machine operators can execute the standard RS-274 programs or specific codes, whatever you design. Typically, these programs will be called only from motion programs under a single coordinate system. See, if it's a standard machine, there's only going to be one coordinate system. But you can run multiple coordinate systems in Power PMac. So if you do so, you can number the coordinate system to the ldata.coord. For example, you can define a local variable, local this CS coordinate system, this CS equal to ldata.coord, and the coord in brackets this CS dot no blend equal to 1. So you will know the coordinate system number. So this is an example for the G code program. So this is your subroutine that the integrator has to write, and an M routine. So let's look at this G code subroutine. For example, in the part program you have G01. That means in RS-274 code is linear interpolation. Puts the machine in the linear interpolation, right? G01. So that G01, when the PMac sees it, it's going to go to subroutine number 1000, subroutine program 1000. So it's going to go here, open subprogram 1000, and G01 times 1000 is the line number 1000, right? So it's going to go to the line 1000, one number, N1000. See, now you're introducing the linear command. That's the PMac command, right? So now you're putting the machine to the linear interpolation. And then it's returned. So it will go back to the calling program, your part program. So you have all those covered in here. G00 covered in the N0 as rapid mode, return. G01 linear interpolation, so N1000 colon linear return. G02 is the clockwise circular interpolation. So you need to use the circle command in Power PMac. So you go to the line number 2000, N2000 colon circle 1 return. G03 means counterclockwise circular interpolation mode in the standard G codes. So then you have to go to the line number 3000 and 3000 colon, issue the circle 2 command in Power PMac, and then return to the calling program. G04 in G code, it's a delay. It's like dwell time, your waiting time. Generally, it shows with the P. You will see like P2 in the standard program. That means wait for 2 seconds. So how can you interpret in Power PMac this? You can do this with the dwell, right? So when you see the P2, it's going to go G04 and then P2. Then it's going to go to line number 4000 and 4000 colon, read the P letter. It's going to read. It has to read. This is a new command. Maybe you haven't seen it. Read the P. We have, for example, G04P2 here, right? So it has to read that P. And this is a little bit tricky, but easy. So you read it like this. Whatever you read it, it's going to the register D0. So you're checking this P is the 16th letter of the alphabet, right? It's 16th letter of the alphabet. So, and D0 register is the whole thing. P is the 16th letter. So now you're checking the D0, this is the whole register, and the 2 to the 15 of the bit, which is the 32,768, right? 2 to the 15. If you check this in the if statement, you're going to see if that bit is high or not. If the bit is high, you have successfully read it. So that's why you want to check this one. Did I successfully read this P command with the D0 and 2 to the 15, bit number 16, is it on or not? So if it's on, you have successfully read it, then you can issue the dual command in PMAC, dual D16, which is going to be the 16 letter, so it's at the D16, the register. D16 times 1,000. The 1,000 coming from, you want to convert it to second, right? With dual, it's in milliseconds, so your part program giving you in seconds, so you want to be in seconds, you need to times 1,000. And then else, if nothing is readed, you want to make sure you don't wait any, you don't wait in here, so you issue a dual 0, then return. Is this clear? This is how you read successfully letter in PMAC. For example, let's look at this, the G97. G97 is a spindle speed in standard code. So it will tell you G97, then S2000, 2000 RPM. So you want to set, you're going to go to the 97,000 and colon read S, and you want to check now the S is the 19th letter of the alphabet. So you're going to say if D0 and 2 to the 18, if it's 1, then you set the motor jog speed to D19, right? That's the 19th letter, so D19. And you have a conversion here from RPM to counts the motor units per millisecond. Then return and close. So if this is clear, all of the rest is the same. G17 is the XY plane for circular interpolation. So you go to N17,000 colon normal. You select the normal, K minus 1. G18 is the specified ZX plane. So you go to N18,000, selecting your normal, J minus 1. G19, I get just selecting your YZ plane, go to the N 19,000 normal, I negative 1. Then G90 is absolute mode, so you just need to issue the absolute command. G91 incremental mode, you need to issue the incremental command in Power PMAC. And this is pretty much cover the basic G codes here. So this is a typical subroutine 1000. And the M codes is same as this one, except you write them into the 1001, right? Open subprogram 1001 and start spindle clockwise. That is M03. So M03, you're going to go to the line number 3000 and jog in positive. Return. That's spindle in clockwise start. If it's M04, start spindle counterclockwise. So go to the line number 4000 and jog in negative direction. Whichever motor you assigned, right? This is motor 4, so we assume the motor 4 is our spindle in this case. And if you want to stop the spindle, then you go to this is M05, so you go to line number 5000 and jog / for that motor number 4 in this case. Okay, if it's clear, we can see the part program. So this is our part program. You define 3 motors for the CNC machine. You don't need to put the spindle in the coordinate system, right? So you have only motor number 1, 2, 3 in coordinate system 1, and motor 4 is like a spindle. It's independent. So you just gonna jog it. Your part program, you homing all the motors first, bringing machine to a starting position, and see G17, G90. So you're choosing your plane, XY plane, and you're putting in the absolute mode. Then you're setting the spindle G97, S1800. You're setting the spindle to 18 revolution per minute. Then your cutting speed F500, feed rate, and we're gonna gather this data. So begin gathering and gathering here, we're gonna plot it. And then you have a rapid mood mode, G00, X10, Y5, Z5. Then you're starting the spindle with M03. Then you're waiting for 2 seconds, G04, P20. Then you're putting in the linear interpolation by G01 and lowering the cutter Z0. And then you're executing some motion here. So at the end, this plot will look like this. You're going to cut a shape like oval. When you execute this one by #1 B part program example run, put all the 3 motors in the closed loop, run this program, you need to see this plot